work done by non-conservative forces. That means friction. Well, you're going to find out quickly that if you calculate the total energy at one point and the total energy at the other point, they will not equal to each other if you have friction force. So for example, if a leaf falls off a tree, there's a tree here. We have a leaf. There's the leaf. It comes loose. It really just attached there. Suddenly that dies and it's going to fall. Foliage season is going to be here sooner than you think. Let's say the leaf has a mass. Oak tree leaves are heavy. I don't know, 17 grams. That's 0.017 kilogram. I have a lot of oak trees in my yard. Each leaf is like a foot by a foot, almost like massive. So they have a mass to them. And the leaf was, I don't know, let's pick a height, 5.3 meters. Two significant digits for each one. Good. And it's gliding down. You know that leaf is so big, it's like a foot by a foot, so you get the air under it floating it. Just like when you drop that piece of paper, it's not falling like a rock. It's slowly. So right before it hits the ground, that leaf now have a velocity right before it touches the ground of 1.3 meters per second. Now, if we look at the potential and the kinetic up there, potential and the kinetic down here, they will not equal to each other. Let's see what they are. Let's call this A, call this B. What is the potential energy at A? It's the mass, which is 0.017, gravity, 9.8 times the height, mgh. Height is what? 5.3. And the kinetic energy at A, it's 1/2 the mass times the velocity square. Well, when the leaf was attached there, the velocity was 0. So that's a 0. 0.017 times 9.8 times 5.3, which is what? 0.88? 88298. 88, two significant digits. So when I add them now, the total mechanical energy at A is going to be the potential plus the kinetic, 0.88. Yep. Now you're going to find out the energy here, actually the total energy is less than what we started with. Friction is going to make you lose some of the energy. So let's look at point B. What is the potential energy at B? That's your final. It's mass times gravity times height. What was my height there? That's a 0. And my kinetic energy at B is what? 1/2 the mass times the velocity squared. And the velocity is 1.3 squared. And it better be less than 0.88. I got what? 0.0143. You know, I'll do 3 significant digits here, just to show. 0.14. So what is my total mechanical energy at B? Is 0.014. Are these numbers the same? No. So actually we have work done by the non-conservative force. Work done by a non-conservative force. We're talking about friction. and the work done by the friction force is negative. That's energy lost. How much is that? It is the final, which is at B, minus the initial, which is at A. This is where you were initially, this is where you are finally. So it's B minus A, not A minus B. This is where you started from, this is where you end at, the final minus the initial. What's my final? 0.014. What's my initial? 0.883. The difference between them is what we lost.
Negative.
Yep.
869.
0.69.
869.
0.869 joules.
So mechanical energy would be half the unit joules.
What is it?
The mechanical energy would have the unit joules.
Yes, because that's the sun, just energy.
And
All of these have joules, joules, joules for a unit. Every one of them. Okay. Trying to think, like, I don't know trying to think of the number, the coefficient of friction between the water and human body. Because I'm trying to think of an example where somebody jumps off the diving board, into a deep pool, and you go into the water and it slows you down. And as you enter in the water, that's why you stop, you don't touch the bottom. Because as you're going through the water, that water is just rubbing against your body, slowing you down. I don't know what the coefficient of friction for that, so we'll make a number for it. We'll pretend we know the numbers. Somebody actually standing on a diving board, we'll say 10 meters high. That's a big diving board. Doesn't jump, steps off the diving board, hits the water, So it steps like this. When it lands, like that. Now he's going to travel through the water. That person, the water is going to stop you. So this is the pool, deep pool. He never made it, or she never made it, to the bottom of the pool. They went this far. And they came to a complete stop. Final speed here. The question I have is, how far? What's that distance will travel in the pool before they come to a stop there? What is that distance? What's that height, distance, whatever you want to call it? I'm going to neglect the wind resistance, only deal with that value there. Wind is not much. So if I'm the person designing this pool here for the Olympics, I say, I've got to make sure the person's going to be jumping from 10 meters high. I know what the coefficient of friction, so I'll find out the lowest number possible that somebody actually shaved, they have not a single hair on their body, slick, their body smooth, and they even put Vaseline on it to slide through the water, which is probably illegal. I don't know about that. If you can put that on your body, I don't know.
Baby oil.
But I'm going to look for the smallest number, because if it works for the smallest number, it will work for anyone after that. So for safety purposes, I'm going to find the smallest value. So let's see the coefficient of friction here, mu k, that's mu, coefficient of friction, kinetic, you're sliding between the body and the water. And I wish I know the number, so I'm going to just wild guess, I have no idea. So that height might be 50 meters, the pool, because I'm just guessing on that number. Let's say it's 0.3. Wild guess.
5 feet what?
So we'll see what distance is. So how far is the person going to travel through the water before it comes to a complete stop? The diver. If there is actually no wind there, if I use this as reference, up there, no friction, that means your energy here should equal the energy here. If I say no friction on the top, but once you enter the water, there is a friction. I'm just neglecting the wind. As you're coming down, you know the wind is hitting you, slowing you down. That's even better for my design. Because if I'm making that zero effect, it's going to go deeper. So I'm leaving some room for me, so in case somebody really does something crazy and they just keep going. I only have on the top what? Only potential energy. Why? Because that person stepped off the diving board, didn't jump up. So your velocity here is 0. So what do we have for potential energy at the top here? Oops, I don't use PE, I use mu, or U, not a mu. It's mass times gravity times height. And again, if I'm designing this for the Olympic, how would I know what the mass of the person is? Every diver has a different mass. Well, it doesn't matter. Doesn't matter what the mass is. That's 98 m. What's my kinetic energy? 1/2 mv squared. That's 0, because the velocity is 0. So what's my total energy there? 98 m. Right before I enter the water, if I neglect the wind, what is my total energy right before I enter the water here? 98 m. Same as the top. Anywhere from here to there is the same thing. Now let's look down here. The person hits the water and slides down through the water all the way to here. What is my potential energy down here? Mass times gravity. What's the height in relation to that one? Negative what? Negative d. And he probably didn't have to give you the coefficient of friction even there. What is my kinetic energy down here? 0. Stop moving. I'll keep going. So what's the sum down here? Yep. Negative 9.8 md, right? What do we know about these two numbers? They should equal to each other. Oh, wait a minute. Good call. Even with the friction? Because if there's no friction, how far is he going to go? 10 meters. Is that the only thing there? What about the friction, the work done by friction? They can't equal to each other. Why? Because you're going to lose some force due to friction. Well, wait a minute. How much did you lose that energy? You don't have all that energy. When you lost a lot of it along the way. We lost to friction, work done by friction is what? The work by friction, work is what? Force times the distance. And for friction is always negative, it's backward. But what's your force? Isn't that your weight? The weight, which is what? The kinetic friction, it's actually mu k times n. That's the friction force is mu k, so I should say F friction here, times the distance. Well, the friction force is mu k times n times your distance. My mu k is 0.3. The normal is what? That's your weight, which is mass times gravity times the distance d. And that should be a negative also. We're losing that, you know. So that energy I had with me here, the 98 M, I had before I enter the water, should equal to what? The energy I have once I'm at the bottom of the pool, this energy, plus all the energy I lost here. The minus just tells me I'm down here and losing it, so the value of that is negative, so I don't have to put the negative. That means that's what should be. Plus what? Whatever I lost here, which is what are these numbers when you multiply them? What's 0.3 times 9.8? 2.94? And notice the m's actually cancel each other out because it shows up in every one. So subtract 9.8 from 98. 88.2. Go ahead.
Is there still a D?
Oh yes, they all have. This has a D in it?
Yeah.
Oh, my mistake then. I gotta add those two, yep. My mistake. I missed the D there. Get too excited. 98 equals
12.74.
12.74 D. D equals what? 98 divided by 12.74. The pool has to be 7.7 meters deep. To make sure the person actually stops before they hit the bottom of the pool. But you are going to lose whatever that energy you had with you, which is this one, you're going to lose all that friction, the work done by friction from it, and whatever left is going to equal to that one.
So when they're designing the pool, did they just make it like extra deep?
For those, yeah. If you've seen actually these pools, they are, again, I'm not sure if they will be deeper than normal pool. The answer is yes, but I'm not sure what the coefficient of friction. So because if you know what that number, if that number was 4 or 5, just to give you an idea, if this was a 5 here, that changes that number and makes it less deep. I don't know exactly what the coefficient of friction, but yes, the answer yes. For the higher you are, the deeper the pool is. You have to. If you only make it like 2 meters, like most pools, they'll all have broken necks or broken backs, legs, everything. But as you enter the water, that's how you stop. You know, the friction coefficient is helping you lose that. Yes.
But that's when the person stops in the water. That's
Correct.
not how-
So the depth is it below the surface 7.7 meters. You know, I could use minus for these numbers, and they'll say negative, which means below that. The negative just tell me it's below that surface. You know, so if you remember, this is where the friction force gives you a negative value, and that's a negative. And I didn't use the negative because I know it's below that line. So 7.7 meters below that surface, the surface of the water.
Work done by friction always negative?
Coefficient, I mean, for a non-conservative force, yes, it's friction you're going to lose. It's always a negative value. So when they ask you how much work done by the friction force, you really should put a negative for that one. That means you lost it, you know? So if you put a negative here and negative there, you end up with D being negative. And negative D means you're below the surface of the water. So if you want to be technically matching our book, these numbers are negative because that's friction force, always negative work, energy lost. So both of these will be negative. Remember, this was a negative, and this will be a negative. So if you want to match our book in terms of answers, so you're still adding these numbers, but they are negative values. And what does the negative means when you see that negative sign? It's below the surface of the water. That's all that means. Because I use this as reference. Anything above that is positive, anything below that is negative. I knew that, that's why I just dropped the minus sign just to make the math easier for me. But if you want to be correctly, like in physics, or match our answers on the software, work done by friction is always negative. Always negative. Why? Because you're moving forward, or the force is forward, and the friction force is which way? Backward. So the person is sliding down the water, but the friction force is pushing upward. That's why it's a negative value. The same thing when you watch a golfer plays. I was watching golf on TV yesterday. They hit the ball. You see the ball moving. It slows down, slows down, slows down, stops before the hole. Well, why did it stop? Friction force. The work done by the friction force is taken away. It's negative. We're losing that energy. Because when the golfer taps it, when Baba Watson yesterday was playing, and he hits the golf ball. Hey, let's say he has a big putt to make. There's the cup here.
Do you think there's actual strategy in golf, or you just hit it and hope for the best?
Oh, no, no, no. Trust me. That is the most scientific sport there is. They gotta read the grass, which way the grass. That's why you see them sometimes. If they're thrown, they want to drop it there. They don't even hit it this way. They go like this and let the grass, like the way the grass is cut, take and drop you that way. And the way the contour of the earth, the way I mean, not just the earth, even the hole itself there. Because some of them are on the top, some on the bottom. So if you're on the top, you're making you roll backward. If it's on the bottom, you get to the top and let it roll down. So there's a lot of science in that. Yeah. Yeah, I wish you would just close your eyes and hit it. No, no, it's not like that. If you just always hit it toward the hole, you will never make it. Nope. You see these guys looking at it and reading it and bending down, looking to see which way the grass is going.
I mean, I'm pretty good at mini golf, and I just hit it, so, you know.
And it goes in, huh?
Yeah.
Yeah, that's it.
Exactly.
So when they hit the ball, initially the ball is sitting here, you tap it, and initial velocity, let's say, I don't know, it's 5 meters per second. Get a nice putt to make there. The ball, and right before the hole stops here. Velocity is 0.
That must be an amateur.
Yeah, you'll probably go shh, and we'll roll down another 50 feet
That's
beyond.
what I do, I bang it
Yep,
on the back, and
yep.
it goes in.
Bounce, 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 bounce till it goes in. So what happened here? Why did it stop? Because as it's rolling, the grass actually is slowing you down, the friction. Because if you look right here, there's no change in potential energy. Potential, if I use this as reference, your potential is 0 on both cases. What's your kinetic here? Kinetic is 1/2 the mass. I'll just leave it at mass. I'll give it a number. I don't know. I don't know what the golf ball, mass of a golf ball, but we'll say it's 10 grams. I'll give you a number. 0.01. Velocity is 5. And you square it. 0.125, I think. I think that's 0.125. So what's the total energy there? Yep. Here, my potential is 0. What's my kinetic? Also 0. What's my total energy here? 0. Well, we know the work done by friction is equal the change in them. It's the final minus the initial. And you'll notice it's negative. What's my final? 0. What's my initial? 0.125. So the work done by friction force, negative 0.125. Negative. Now, if I know the length of the putt there, I can figure out what the coefficient of friction. Let's say this putt was 2 meters long, about 6 feet. What's the work done by friction? Well, the work done by friction, we know the number, but that's equal what? F friction times the distance, and it will be negative because the ball is moving to the right, the friction force is backward, so it's negative F friction times D. What's the friction force? Mu K times N, right? And times the distance, which is what? 2 meters. N here is equal to the weight, mass times gravity. Mass is what we said? 0.01. Gravity 9.8. This is 2. Now we can tell you what the coefficient of friction, the minus signs will cancel each other out. .02 times 9.8, 0.196 mu K. What's mu K? I got 0.64. That's between the grass and the golf ball.
A golf ball is 46 grams.
Is it really?
Just so you know.
Well, it's
I looked
heavy.
it up.
46 grams?
Yep.
Yeah, I made 10 grams really light. So if we put 46 grams, that changes that. Yeah. Yeah, ping pong. Maybe. Actually, when I use my practicing outside here on the green, sometimes I go outside, hit some of them. They yell at me for hitting these balls, so I use ping pong balls. So I have tons of them in my bag. So I take the bag and I go outside and I start hitting them.
Will
Yeah.
you dent them?
Well, if it's $10 for 10 of them or 6 of them for $1. If I dent them, I just get another one. So when you have friction, you can't neglect the friction. You got to subtract that. We'll do one more example. And we'll take, any runners here? Oh, people run? Not me. So we got this person who is an 80 kilogram, want to run a marathon. But here's the marathon. It looks like this. Uphill. So the person is running, starts from rest. So that's the person. Let me give you a mass of the person. There's a lady. Got the long hair, the flowy hair. The mass is equal to 80 kilogram. Starts from rest. Initial velocity is 0. And runs into stiff breeze going uphill even. Oh boy. At the top of the hill, how high the hill. We're not sure yet. At the top of the hill, the jogger has done a work. The jogger made it to the top of the hill right here. The work done by the non-conservative force, non-conservative, NC, is equal to plus 1.80 times 10 to the fourth joules. I'll explain what that is. The work done by the wind. Remember, she was running into stiff wind, stiff breeze. The work done by the wind here, the breeze, is negative 4,420 joules. And when that jogger reaches right there, we know the velocity or the speed of the jogger was 3.5 meters. Probably the question, how high? Yep. What's the height of the hill? How high that hill? What is it? Okay, let's see, what do we have? Right here, what do we have? What's potential energy? Oh, God. Bad habit. P, am I right? P for potential. U equals 0, if I use this as reference. And kinetic is what? 0. Initial velocity is 0, right there. Right here, the top. I'll use a blue color. What's my initial velocity? My potential energy? Mass, which is what? 80. Gravity, which is what? 9.8. And the height is unknown, right? We're looking for it. And what's the kinetic energy? 1/2 m times v squared. Mass, well, we know what the mass is, 80. Let's put 80 here. Times the velocity squared. What's the velocity? 3.5 squared. What's the sum? Let's see.
First one is
40 times 3.5 squared. That's 490 plus, you see, what's that number? The potential?
U was, I got 784.
784H, right?
Yeah.
Notice, what's the sum here? 0. It says, as the person ran there, the work done by the non-conservative force is plus. That's the person, the runner. He also lost how much? 4420. So the net work, W net, or total amount of energy, is going to be what? That's actually 18,000. When you look at that, is that 18,000? 1.8 times 10 to the 4? I think it's 18,000. Minus what? 4420. $13,580. That has to equal what? The final minus the initial. My final is what? The 490 plus the 784H minus my initial, how much we had, which is 0. If there was no wind here, remember the example says stiff wind, breeze. If we didn't have any breeze, this number will be 0. That number will be the difference between these two. But the breeze actually, when you're running against the wind, you feel it. You're running, but you're not going as fast because that wind is pushing you backward. You're losing that energy. That person was working really hard. He didn't get, or she in this case, she didn't get all that energy to be used for her. Some of it was used to fight that stiff wind. So you lost that much from it. So when you look at that, there's only one equation. Subtract the 490 now. So I got 13,090 equals 784H. And what's the height? That height was 16.7 meter hill.